Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a fourth video in a series on definite integrals and introduction to them for you who are likely in a differential calculus course or maybe at the beginnings of an integral calculus course. It's nice to see this actually in differential calculus because it's a really nice stepping stone into integral calculus. But in this video, we're going to talk about the properties of definite integrals. It is assumed that you know what a definite integral is and that you know how to evaluate definite integrals using limits. Now we're just going to get into some sub-properties that are kind of necessary. So this first theorem, the ability to integrate a function, which is called integrability, you could just call it the ability to integrate. If you can integrate a function, then that means that integral is equal to the limit of the Riemann sum. So if f is integrable on the closed interval from a to b, then this notation, which we've already defined to be the limit of the Riemann sum, is true. So if somebody says that you have an integrable function or an integratable function, if you want to call it that way, because I think it's integratable is actually an easier way of saying that, even though that's not how that's spelled. But anyway, if you have a function you can integrate, then it's the limit of a Riemann sum. That's what the integral is. We kind of know this already, so this is talking in circles. This is just nothing huge here. And that's also why, as a theorem, I don't bother proving this, because this is the result of the definition. Now, this theorem I write differently than a lot of authors will. They will say if f is continuous on the closed interval, then you can integrate it. It's integrable. It's integratable. I don't know. On the closed interval. However, there is more to it than that. If f is continuous, definitely you can integrate. And you can build a definite integral for it. However, you can also do that if f has a finite number of jump discontinuities. So it's not just the case that that continuity is required for you to be able to integrate something. You can find the area underneath a curve, of course, if it's continuous. However, you can also find the area underneath the curve if it has a jump discontinuity or a finite number of jump discontinuities. You can totally do that. So if you had something like from A to B here, you could slice it in such a way that it would look like this. And that's perfectly fine. You can find the area underneath that curve. There's nothing wrong with that. As long as it has a finite number of jump discontinuities, you could totally integrate or find the area underneath that curve. So that's my modification to that theorem. Again, I'm not proving these theorems. I'm going to justify the next one though, or justify parts of it. The next one that we're about to see is the biggie. And I mean that literally. It's a huge theorem. So the properties of definite integrals, and all of these require some thinking. So we're gonna, even though this is only 3 pages worth of a lecture video on my end, it takes a while to talk about some of these because we want to really delve into and figure out why some of these properties are true. For an example, if I want to find the area underneath a function, remember that's what really a definite integral stands for. It's the limit as n goes to infinity of a Riemann sum. And so Riemann sums allow us to find areas between a function and the x-axis, signed areas, right? So you can have negative areas, that's perfectly fine. So this first one right here says that if we integrate in the wrong order from b to a, it's the same thing as the opposite of integrating in the correct order, a to b. Now let's go ahead and see that. I have a little space down below for justifications, not proofs, but justifications, because I think the proofs aren't as impactful as the justifications in these problems. So let's say that this is a setup. We have a function. We have I always write them with positive areas. It actually does not matter whether they're positive or negative areas, but for the justification, it's easier to see that if we deal with this positive area. Now let's think about this logically. I want to start at B and work my way backwards. That's kind of weird, isn't it? That's what this is saying. I want to start at B and work my way backwards. And if you don't believe me, remember, this is the limit of a Riemann sum, right? So it's limit as n goes to infinity of some summation I equals 1 to n of f of x sub I delta x. Here, the problem is that delta x in our case is, remember, upper limit minus lower limit. I've been saying b minus a, but really it's upper limit minus lower limit. So it's a minus b over n, which is, by the way, the opposite of b minus a over n, isn't it? Okay, so if that's the case, we have that this is the limit. I'm actually proving it right now. This is a limit as n goes to infinity of I equals 1 to n of f of x sub I times, we just wrote it out, it's a minus b over n. But again, that's the opposite of the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I times b minus a over n. And if you did it that way, that's the opposite of the integral with the upper limit b, lower limit a. That's the opposite of the definite integral starting at a and going to b. Visually or conceptually, it goes like this. Somebody says, I want to find this area, and they start walking the wrong way. All of their delta x's are going to be negative because you're walking the wrong way, right? All of our little wiggle sizes, it's like, in this case, if you start at B and you need to go backwards, your delta x has to be negative to go backwards. And so in all these cases, you have these negative steps. And then somebody says, you know what? I'm going to find that very same area, but I'm going to go forward. Well, if they start at A and they move forward, their deltas are going to be the opposite of your deltas, right? And so again, you are going backwards. It's the same as them going forwards, but with a negative delta x. Okay, so that's the justification. Also, technically, it's the proof. I actually did the proof down below by accident. Anyhow, so that's the justification for that. That's an incredibly powerful, very, very powerful theorem. It gets used quite a bit. In fact, let's rank these. Not rank, that's the wrong word. I don't want to order them in some preferred order of remembering, but I'm going to rank them as far as I'll grade them as far as how often they get used. This is an A. This gets used quite a bit. Okay. The next one, which is easier to understand than the previous, if I start at A, I have some curve, goes from A to B, but I don't want to go to A to B. I only want to start at A and end at A. Well, if I didn't go anywhere, then obviously the area is 0 because I've gone nowhere. The thickness between A and A is nothing. So I've done absolutely nothing. I hope that makes sense. Unfortunately, as easy as that is, it doesn't get used a lot. So I'm going to call that a D because it just doesn't get used a lot. Although it is very important. This is not their level of importance, A's and D's and stuff like that. It's how often they get used. So unfortunately, as cool as that is, it doesn't get used a lot. This guy right here, the definite integral from A to B of a constant C. Well, that is going to be C times B minus A. The justification for this, I'll write down below before I tell you how important it is. So let's go ahead and wrap this other justification up. We'll just kill it off. And let's take a look at an x-axis here from A to B. And I have a function that's a constant. So I have a function y equals C. Now remember, the definite integral from a to b of that constant function is just the area underneath that curve. Well, there's one big fat rectangle here. The area is width times height. The width here is b minus a. The height is c. And there you go. That's actually the proof of it. So c times b minus a, very, very easy to remember. It does get used. I don't want to say it gets used a lot, but it does get used. I'll give this a C. It gets used, but it doesn't get used a lot. Because rarely do you just have a constant that you want to find the definite integral for. The next one, super powerful. This is an A+. This happens all the time. If you want to find the area from A to B underneath F plus G or minus G, it doesn't really matter, you could break that apart into two different summations. And now this is just a property of limits. So remember that a definite integral is just the limit of a Riemann sum, so it's a limit. And you could break limits apart across summations and additions, or summations and subtractions, if those limits exist. Generally speaking, that's what you're going to be working with. So anyway, this is very, very popular. This allows us to look at something like the integral from 1 to 5 of x squared plus 2 dx and say, you know what, I'd rather look at the integral from 1 to 5 of x squared dx plus the integral from 1 to 5 of 2 dx. That just allows us to do stuff like that. Very, very, very powerful property of definite integrals. Let's see. Next one. This one, I don't want to say it's not powerful. It's pretty darn powerful. I'll give it a, let me use green ink here. I'll give this like a, I'll give this a B. It's a really good property if you can use it. So the visual of this is really neat, but I'm going to say it out loud first. And I'm going to start over here, actually. You have a function, and you're finding the area under, in quotes, that function from A to B. Well, that's the same thing as starting at A and stopping at C partway through, and then picking back up from C and going to B. Let's see this in a picture. It's actually really nice once you see it to understand it. So looping that up, killing that off, let's go ahead and just draw in quick function. So here's our function, typical. Actually, you know what? Let's do something like this. There we go. There's our function from A to B. And let's pretend that here's some point in between called C. Okay. Well, the area underneath our function from A to B of f of x dx, it would be all this negative area plus all of this positive area, right? I hope you would agree with that. But you could say, you know what? I just have a problem with doing that all at once. So I want to do from A to C first. So you get this positive and this negative area. And then you say, to that, I'll add the integral from C to B, f of x dx. So in that case, you would add on this little extra bit, actually this large extra bit. But shaded, it's the same region that's shaded, or area that's shaded from the first integral. So there you go. It's a very nice way to do it though, because you might actually want to split the integral into pieces for some weird reason. Actually not weird reasons, honestly. You might do it because your function's periodic. That ends up being very powerful. We'll see examples of that later. So again, very powerful, does get used. Now the next 1, 2, 3 theorems, or 3 parts of this theorem, don't get used all that often. So again, none of these are useless properties, but just some get used less than others. This first one, if, whoops, that was supposed to say f of x. So if f of x is non-negative for all x, then the area underneath it must also not be negative. That's really what that says. Actually, let me write that down. There you go. And that is somewhat useful, but doesn't actually get used that often. I'm going to give it a C- because it doesn't get used that often. It is powerful, but it's just not a lot of people find good uses for it. The next one's kind of like a squeeze theorem in a way. Well, actually the last one's like a squeeze theorem, but this one right here, f of x, if you have a function that's greater than another function for all x values on an interval, then the area underneath the greater function is greater than the area underneath the smaller function. That's really what that means. A visual of this actually would be kind of nice. And this time I'm going to twist your brain a little bit, because normally I would do all of these justifications with positive functions, but why not? Let's do something slightly different. So here, I hope you can agree, our function f is greater than our function g on this interval. They're both negative, but f is less negative. How's that? So f is above g on this interval. Now, if I were to find the area underneath f, so in this case, f is greater than g. If I were to find the area from a to b underneath f, when I say underneath, it's a signed area. So this area right here is a negative area. It's definitely negative, but it might be like a -5 or something like that, right? So that area I shaded in there is negative, and I shaded it using 5 gallons of paint or something like that. Well, I hope you can agree that is going to be slightly larger than the area underneath g, because the area underneath g, I'll need 20 gallons of paint for, and it's negative. So that's like a negative, let's just pretend -20. And this is, let's pretend -5. -5 is definitely greater than -20. There you go. So that's not a proof, that's just a justification, but it's a visual justification. It shows you that if a function's bigger than another function on an interval, then the definite integral of that function is bigger than the definite integral of the other function on that interval. There's a lot of INs in that statement. Does this get used a lot? No, it really does not. I'm going to give it a C- as well. It's unfortunate because it's kind of cool and visually very easy to understand, but unfortunately just doesn't get used a lot. Of all these last three, this one probably gets used the most, although it still doesn't get used a lot. It's good for approximations. What is this saying? Well, if I know my function has heights between little m and big M, then I've found a bound on the definite integral. Before I even focus on what that bound is, I want to show you the bound, because this one is super awesome to see. So let's suppose that you have some function, my typical function, here it is. Okay. And let's say that we're going from B to A, or A to B, sorry. So from A to B. And let's also suppose that on that interval, here's the y-axis, the highest value, I'll put that in green, that the function attains is called a capital M. And the lowest value the function attains, I'll put that in red, which is right about here actually, because that's not lower. The lowest value is a little m. And I'm saying I need to figure out what the area underneath this curve f is. So there's f right there. I'd love to find the area underneath that curve. Well, I hope you would agree that area is bigger than this block right here. That should make sense. The area underneath f, which is the definite integral, so the integral from a to b of f of x dx, I hope you would agree that is greater than or possibly equal to, if f is the same as this height, but it's greater than or equal to the area of that red block, which is m times b minus a. Well, what if we wanted to consider how big the area could be? Well, the area underneath f, the maximal area underneath f, the biggest it'll ever get is the area of this green block right here. In fact, it will never actually get that big. I shouldn't say never, but it likely will not get that big. So the area underneath f must be less than that green block. So it must be less than that green block, which has a width of b minus a and a height of capital M. And that is actually what this statement up here is saying. So there you go. Again, I've ranked all these in terms of not in how I rank them in terms of how often they get used, but they are all very important. Obviously, the most important would be the splitting apart an integral, and then that one using the opposites, right? You can swap limits of the integral as long as you pop out a negative, essentially. So, in the next video, we're going to use as many of these as possible. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.